Okay. Welcome, everyone. Thank you for joining us for this discussion on trusted execution environments and verifiable AI. I think just broadly speaking, as AI systems become more integrated into critical decision-making processes, basically ensuring integrity and trustworthiness is going to be much more salient as we think about AI as a whole. Trusted execution environments, I mean, they've been around for a while. You have hardware chips like Intel SGX, AMD, SEV, ARM, that offer kind of more of a hardware-based approach to processing sensitive data and computations in specifically secure environments of the hardware itself. And then on the other side of things, we have verifiable AI, which uses techniques such as remote attestation, zero knowledge, MPC, consensus-based models that ensure computations and outputs independently auditing or kind of proving cryptographically. So, these technologies have been explored in kind of a great depth over the past year or two in particular, and will no doubt increase in significance over the coming few years as we see a greater integration and application of AI into more sensitive systems. And with us today, we have an awesome team of panelists with a great breadth of experience from all different kinds of companies working across this stack of verifiable compute in some sense. So thanks for joining everyone. And why don't we just start out down the line, and if you can introduce yourself and some of the work that you are doing, we can kick off like that. Jorge, if you want to start off.
Hello. Can you guys hear me? Yep. Okay. Thank you very much. My name is Jorge Arce. I am a blockchain and cryptography researcher at Nethermind. I've been with the team for close to 3 years now. I have a background in mathematics. And at Nethermind, I had the opportunity to research on a lot of interesting blockchain primitives, mainly around staking, restaking, and also how that interplays with artificial intelligence security, and now AI agents as well. Some of our teams at Nethermind have been working on and championing various TE initiatives, so that's also something we can discuss as part of the panel. But yeah, excited to be here, guys.
Hello, everyone. I'm Han from Phala Network. So Phala Network is a TE network. Basically, you can see it as the AWS, but all running in the TE, built for Web3 and the decentralized AI. And before I created Phala Network, actually Phala Network is a really old project. It has been running for 6 years. And before joining Phala, I worked in Google. And it's pretty funny. I work in Google to spy everyone's Gmail. So all your Gmail was scanned by some algorithm I have developed when I was in Google. And I figure out, I'm enough with that. So after 3 years, I totally jumped into the ops side. I think this is like Web3. The user privacy matters, collaboration matters. This is where I found I really have the passion about. Thank you.
Hi, this is Zinal. I work with AWS. I'm a solutions architect. I'm a principal. I've been with AWS for the last 13 years. I'm responsible for the Web3 startups. So I work with a lot of Web3 startups directly day to day. And that's why I'm here.
Hi, everyone. My name is Miguel, co-founder and chief scientist of Nillion. At Nillion, we're building a blind computer, which is a new type of infrastructure, Web3 infrastructure that enables you to compute and store personal information, private information. And essentially, my background is at the intersection between engineering and PhD in maths. And what we're working now, one of the things we're working at, is at the intersection between TEs and other privacy-enhancing technologies like multi-party computation and FHE.
Hi, everyone. I'm Ranvir. I'm the co-founder of Witness Chain. At Witness Chain, our goal is to bring blockchains and AI, all digital protocols, to the real world. So then what we're building is a verifiable observation layer that can be used by AI agents. So think of this as physical world APIs. So you can get data, on-chain data, you can get data on the internet, but we get data which is in the physical world in a verifiable manner.
Awesome. Thank you, guys. maybe just to start off, it'd be great to set some primary context. At a high level, open to anyone who kind of wants to take it up here, could you describe a bit kind of what TEs are useful for and maybe some of the other popular encryption techniques which you'd outlined as well, like multi-party computation or homomorphic encryption, and kind of like a high-level overview for the rest of the group?
Yeah, I guess functionally speaking, you can put the three of them like TEs, fully homomorphic encryption and multi-party computation at the same level. What they do, you can think of them in terms of a black box that actually is able to compute on data without seeing it, without having access to it. But they achieve that in different ways. The basic trust assumption behind TEs is a hardware-based one. So you're trusting the manufacturer of the hardware. And with the other two, with FHE and multi-party computation, what you're trusting is actually the maths, so the cryptography behind the solution.
Right. So
Go for it. Yeah.
now maybe just to add to that, so despite the three of those technologies achieving similar goals, it becomes very interesting to think about the different trade-offs that you get into that make one tool the right tool for the job or the wrong tool for the job, right? So for example, with TEs, we have the advantage that they can be a lot more performant in their execution, but the trust assumptions that you're putting on the hardware itself go way up. Whereas when you're using cryptographic techniques, such as like MPC or FHE, normally you're going to see you're not trusting the hardware anymore, you're relying on, mathematics essentially, or like splitting the trust across a set of various parties, which is what MPC does. But you're also going to see a decrease in performance, which is, for example, something that happens very common with fully homomorphic encryption, which essentially allows you to compute on arbitrarily encrypted data, but it can be very, very slow, especially for certain use cases or if you want to do it on chain or so. So sometimes you have to think very carefully about the trade-offs and what's the right tool for the job. Sometimes, for example, you don't even need fully homomorphic encryption. You can opt for like a partially homomorphic encryption variant if you're just trying to like add up results into a tally that is much more performant. So this becomes very much a game of knowing the tools you're working with. So you can pick the correct one. It's not necessarily that one is strictly better than the other. And it's what makes like this kind of like blockchain and cryptographic design such an interesting field.
I can add a little bit to the TE side because we have been working on TE for a long time, and TE actually has a lot of generations. And now I would say now it's the TE 2.0. And at the beginning there was TE 1.0. That was Intel SGX, and now like Intel TDX or AMD SEV. I would say a lot. You guys already mentioned a lot of about their difference. One point I want to add is. TE actually have the biggest difference to me is that it has a really great developer experience. So you can imagine you just have some program, maybe even developed by yourself, throw it into a TE, and boom, it just work within a few clicks, just a few seconds. So yeah, this is one of the benefit of TE I just want to add.
Just following up to Todd logic, historically we always have the hardware isolation, we always have the securing cryptographic security of the secrets, we always had those things. But what's happening with the TEE is that we now have the execution and the attestation coming with it. The computation coming with it is a huge differentiation compared to other systems that we had historically.
So I'll provide a slightly different perspective by going into like what kind of security you need. Right?
Yes.
So in our case, to highlight what we are doing is we want to make sure. So let's say if some protocol asks us, how many people are sitting in this event, right? So somebody can take a photo to prove it, right? But it has to be associated with multiple types of security. You need to make sure that that photo was clicked at the right time. So you need verified timestamping. And that's what blockchains are used for. TEs have limitations that you can't do distributed timestamping natively using one machine. The second thing we want to make sure is that the data actually was collected by a sensor, a camera sensor, rather than it being collected through some synthetic means like AI generated. And for that, we rely on trusted hardware to make sure that whatever data we are collecting actually came from a sensor rather than it being generated artificially. And the third thing we need to prove is whether it was clicked at the right location. Right? So you don't want people to fake locations and claim something else. And for that, we require a distributed set of nodes to do active measurements over a network. So we run what is called a proof of location to verify it. So you can see in our stack, we use 3 different technologies to achieve the security. TE is part of it, where we make sure it's not used for compute, but it's used for making sure that the data actually comes from a sensor.
Awesome. Yeah. Anything else to add?
Yeah, I would like to dive a little bit deeper into what Jorge was saying.
On the trade-offs
On the
specifically.
trade-off space.
Please.
Sometimes, sometimes you don't have to look at that as in terms of a binary choice between, either software-based cryptography or hardware-based. There's also the possibility to actually combine them. So we've been working, for example, on providing private RAG, so retrieval augmented generation, in a mixed solution that uses some part of MPC and storage in the form of shares. And then part of the computation is done in the TE. But actually, the part that goes into the TE is not revealing anything about the vectors, but just some distances related to them. So you're minimizing the amount of information that is actually processed inside of the TE, but you're doing the hard work that would take a lot of time in an MPC or FHE setting, which is the comparisons inside of the TE. And another example is inference. So we're running inference using split technique, whereby some of the elements in the layers, the complex ones, like the activation functions, they're running inside of TEs.
Yep.
That is the slow part. But then the other ones, the linear layers, they're running inside of MPC or FHE. So in doing that, and in choosing how many things you run inside of a TE versus inside of MPC or FHE, you have like a slider that enables you to fine-tune between performance and security. And I think that's a very interesting concept.
Definitely. I think uniformly, it's pretty interesting to see that kind of across the spectrum of technologies. It's a good way to put it, right? You're going to have trade-offs in terms of what's easy to use, and where there's more off-the-shelf development versus what I guess is the most computationally secure. Although the overhead is a big question, right? And I think that's as we kind of shift to maybe the next part, which is what adoption looks like in this category. I think that's something serially that is a question that whether it's customers or people have generally always had. It's what do adoption curves for these sorts of technologies kind of look like, right? Because in some sense, customers might be unfamiliar with the security needs that they necessarily need to have, or there's a question of how secure. So would love to kind of hear any thoughts that you guys have on kind of maybe any initial signals of demand that you've seen organically. What sort of indications you've gotten from there, and how you think it kind of plays out over the next 3 to 5 years?
Oh yeah, maybe I can talk about that first. Actually, 1 year before, just last EthDenver, when we talk about TE, most of the people just think, oh, why are you using TE given we have ZK, MPC, or FHE? Because TE is having the problems every year. But now you can see the sentiment has changed. I think it's changed for a few reasons. The biggest reason is the demand driven. So we launched a cloud platform just in December, late December. And just in two months, now we already accumulated more than 600 users, and there are more than 1,500 vCPUs already used in our cloud. So the curve is boom, skyrocket. So that's what convinced me the most. There's real demand. If we break that down a little bit, then there are a bunch of different use cases. A very obvious use case is AI agent, because there are a lot of AI agents. All of them claim they're running in a TE to get some credibility. And indeed, 90% of our cloud users actually deploy the TE AI agent, and they are mostly individuals or launchpads, like meme coin launchpad or AI agent launchpad. On the other side, we also have another service. Well, it's not selling the service, but we're running the GPU TE. So GPU TE means you can have the NVIDIA H100, H200 enable the TE mode. So you can actually run serious machine learning model training and inference. And we do have a few clients working on that as well. Roughly, if you check the revenue, I think it's roughly half-half. Half from the public cloud, purely CPU AI agent, and half of them are running the GPU. Some of them running training, some of them running inference, and across all the entire supply chain of decentralized AI. So you need to have credible training, crypto inference, AI agent, and even data processing. So combine them together, I would say this is a full supply chain of decentralized AI.
So I can go with some numbers. I cover
Definitely.
I cover like engaged startups for AWS for Web3, and last year I had 20 customers. 15 of them were Enclave users. This is like unbelievable. I wasn't expecting like this much. And I think the main...
Just curious, relatively, what was that versus 3-4 years ago?
That was literally zero. Because, like that was so super common. I think that the differentiation is access to technology is it's leveling out. Like in the past, you need to have access to a very specific hardware, very specific library, and you need to learn and know that thing. That's a very expensive experiment. Right now, people just read a blog post, or I can do like Enclave back wallets. Oh, let me do it. Just let me follow step by step. Or I can do MPC using enclaves, like something like that. And it's not just for AWS. Other cloud providers doing similar things. Access to technology is getting easier now. We have a lot of partners who are also implementing the same technology with different means. So the access is increasing. The use cases are very straightforward. It is not rocket science anymore. So the implementation, the number of users are increasing in a level that now it's creating the site industry. People are taking these TEs and creating APIs, building APIs and solutions over it, which is like the next gen. The layer 2s of the TEs are right now in place.
Yeah, we're seeing also, like Phala, incredible demand from the AI side of things. So a lot of people building agents and platforms for agents, and also things around that as well. Like, for example, the need for agents to be able to store private information somewhere, and also the need to be able to orchestrate communication between different agents. So you can build like swarms, and the permissioning layer necessary for that as well. And also we're seeing a lot of interest and demand from DeSci. So DeSci is very interesting because it combines a lot of big data. So you have a lot of information captured, for example, from your wearables, like heart rate or sleeping patterns. You put that not in a TE, because that would be a bad idea, but you put that on a decentralized database that has secure storage, like, for example, based on secret sharing, based on MPC. And then the next thing you do is that you consume that from a TE and you run some computation to provide you with insights, for example. Or you let someone else, a third party, to run computations and get insights, and you can monetize on that. So we're seeing a lot of people also very interested in building that type of solutions.
So in our case, where we see the most applications is in verifying community. So in crypto and in most protocols that have real-world operations, you want to verify your community if you want to incentivize. So you want to incentivize your community, and if you incentivize the community, you have to verify it. A classic example of this is, let's say you want to do an airdrop, right? And in that case, how do you make sure that you are targeting the right community to do that? How do you make sure that the people I'm sending money to are not industrial airdrop farmers, right? And the way to prevent that is if you have observability into, okay, where are these people who I'm sending? Where is my community actually at? Where is that individual actually at? And are they a real person or not? That observability helps incentive distributions a lot. And in the end, most crypto projects and even a lot of Web 2 operations rely heavily on knowing who should I send incentives to, which is the right community to incentivize. And that's what we help with.
Awesome. Any other use cases people want to highlight?
So I think that's been a very good bird's eye view of specific niches. And that's maybe to bring it in, I would say, from my perspective, TE is just booming at the moment, right? Especially with the rise of AI agents, and it giving you such a convenient way to prove that you are indeed dealing with an AI agent, and that the responses, the outputs of the agent are indeed coming from like LLM inference, and not just a human in the loop that is maliciously like injected in answers. So there's a bunch of agents on Twitter that have been let loose, and like say AI XBT and the like. People trust that those are agents, and if you construct them carefully, you can use, for example, TEEs to ascertain that this is the case. Other approaches to this problem involving zero knowledge. If we think about, for example, zero knowledge machine learning, which Miguel was talking about, the fact that doing it end to end at the moment is not quite feasible computationally, especially for a big LLM. So you have to look into workarounds, maybe like split the problem into like put the most complex piece elsewhere. Or there's a very interesting workaround that people have found with zero knowledge under the name of zk-TLS, which allows you to prove that a TLS connection allows a third party to like audit a TLS connection, prove that the outputs of it indeed come from like the TLS transcript, like a connection between a user and a server. And the reason this is important for AI inference is you can use zk-TLS to prove that someone connected to Open AGI's API and like called a ChatGPT, right? So this is like maybe full-on ZK-ML is not usable in production now, but you can use these kinds of workarounds with zero knowledge if you get creative to prove that indeed you're connecting to a machine learning model, right? The long story short, TEEs are already in full swing here. ZK might be a little bit expensive for certain use cases end-to-end, but there are ways to find workarounds if you're creative. Fully homomorphic encryption is one that has a lot of potential, but I think it's also being like held back by scalability and performance. All the teams are doing massive improvements on this as time goes by. So maybe 5 years from now or so, we're going to see it being a lot more commonplace. Just like in the way that Hang was describing that TEEs like 5 years ago or so, like were not as common because there were all of these problems, and nowadays they are just like essentially the first tool you pick off the shelf.
As an interesting use case, I've seen even a PhD student implementing a full exchange matching engine in the TEE so that everybody has a fair access to the trades. So the implementation, like it's becoming so mainstream, like the use case that we didn't hear, a lot of safe room type of flows where like multiple parties access to the same data set without seeing each other's data. And the use cases are just multiplying every day. So like who would think like a few years ago, like you would run a matching engine in a TEE. So now we are seeing like the proposals for that. So.
Quick add up on that. And actually, since this is EthDenver, there's a very interesting use case of TEE that is in the MEV or block building space. So Flashbox is pretty deep in that. Basically, if you want to eliminate MEV, so maximal extractable value, the only way to do that is to putting it in a TEE. All the other solutions doesn't work because people has been exploring that for years. The same time, once we have the TEE-based MEV block building mechanism, a lot of things can be unlocked. Say, you can have multiple searchers negotiate inside the TEE. You can even send your AI agent to represent your strategy into a TEE. They can fight, they can negotiate, but they cannot bring any sensitive information out of the TEE. It's basically a black box. So those all kinds of interesting things, as you mentioned, is maybe come from the data clean room idea, but also has a lot of use cases in blockchain, Ethereum as well.
Some use cases with agents. I think there's like two types of agents. One is the public ones, like tweeting and doing things like that. The other ones are manipulating personal information. And I think those require not only verifiability in the terms that and sense that Jorge was describing, but also in the sense that you need to have guarantees that there's nothing leaking information. There's, the host of running the TEE hasn't introduced any program inside of the VM that is actually accessing the information that the agent is running on or working on. So the attestation also covers for that, which is great. And some examples of use cases we're seeing built are, for example, covering Telegram. So I don't know about you guys, but for me, Telegram is a mess. It has a lot of messages, so it would be great to have an agent just go through that, organize it, create groups for you. But of course, that's really sensitive information. Actually, it is legally troublesome because you're dealing with third parties, and there's probably confidentiality clauses in place. So privacy is of the essence right there. Another example is agents providing you with advice. For example, tax advice, health advice. So one example is you get 2 agents provide you with diagnosis on some symptoms that you send over to the agents, and then there's a third agent that decides which one is the best one. So you get the benefit of the second opinion and a judge that makes the decision. In all those use cases, privacy is of the essence. And so the attestations go beyond just the integrity of the service. You just don't want to be sure that the right model is being run inside of the TE, but actually you want to be sure that nothing else is running inside of the TE so that no information is being leaked out.
I think one thing I wanted to highlight, since we're on the topic of fair matching and MEV, as important as it is to ensure that the computes happen correctly, it's also important that the data going inside the TE happens in a fair manner. So in case of, for example, in case of MEV, you can artificially, for example, introduce delays before your message or your order goes within the machine. Or you can co-locate your trading software to where the actual TE is situated. And that gives you significant advantage over where if somebody else is trading from other side of the world, in case of matching. So I think we need to compose multiple technologies together. You need to compose TEs for fair order matching. You need to compose some geolocation trade-offs to make sure that your end system works. So I think rather than comparing different techniques, I think the right approach is to compose multiple such techniques together. And I think TE is a very powerful tool.
Awesome point. Yeah, I think it's a great point. Composability is kind of the name of the game here, and at a hardware level, like it's secure computing is just gonna become more so the standard. You'll see to your point, like GPUs, like B200 chips are all TEs are going to be a standard in this case, and yeah, as more secure use cases are rolled out, that's where these sort of computations are going to be more relevant. I think we only have a few minutes left, so I guess in terms of closing thoughts, anything you guys particularly want to call out to watch for that we should be paying attention to broadly in this space that you might be working on or otherwise.
I think, continuing on that point, I think we need to look at the larger picture and see TEs just as a building block inside of a larger solution that combines other privacy-enhancing technologies. For example, for storage, you would probably want to use secret shares or encryption on top of that. For permissions, you don't want to do that inside of a TE, but you want to run them somewhere else. For blockchain integrations, you want to be using signatures, but ideally you could thresholdize them, so you could use MPC type of signatures so that the private key is never reconstructed inside of the TE, and that gives you higher security guarantees. And I think it is in that combination of all those pieces that you can then achieve the best out of each one of those technologies and provide really interesting solutions.
Go for it, Jorge.
Yeah. Maybe to point out, in terms of verifiable compute, we have talked about hardware solutions, TEs. We have talked about cryptographic solutions, ZK, FHE, MPC. One that we didn't touch upon at all, which is quite one of my areas of interest, is cryptoeconomic security, so to speak, and what you can achieve with primitives like restaking and the like, right? So this is another way in which, you're essentially, for example, setting up a set of operators to generate a certain computation, and then they have to attest to the validity of that computation and put that attestation on chain. And if the computation is proven wrong by an outside party, you can use this attestation that was put on chain to slash those operators or punish them somehow. And the idea is that if you design this game right and sort of so that the punishment for doing things wrong is greater than the potential earnings from letting yourself be corrupted, so to speak, then a rational actor is never going to go against the system. And this is another way to achieve verifiable computation that doesn't involve any of these primitives we have discussed. It's also an approach that tends to mix well with decentralization. And this is what like EigenLayer and AVSs are essentially doing. On my side, and with regards to like some of the research we do at Nethermind, we are interested in exploring how these verifiable computation services in the form of AVSs interact with AI agents. In particular, whether we can design an AVS to decentralize the runtime of an AI agent itself so that it's running across a set of operators in a way that it's hard to censor or it doesn't depend on single points of failure that can be easily taken down. So I would say, yeah, in terms of like composability and like blockchain integration or such, we also have to think about cryptoeconomic security for verifiable compute and the primitives of restaking and the like. And many of these interact very well with TEEs, for example. So when you mix cryptoeconomic security and TEEs, you can bring or eliminate entirely a whole set of failure modes. So maybe now your operators, if they are running the, let's say, AVS software in a TEE, you don't have to worry about them being malicious or going against the protocol. Now you just have to worry about them, what happens if they turn their machines down. Maybe the only way they have, the only recourse they have to go against the protocol is to censor it, right? But then you have eliminated a huge set of problems, especially if they are dealing with sensitive data. So once again, I think perhaps a good takeaway of this is there's a huge set of tools in the toolbox that we can work with. Hardware, cryptography, cryptoeconomic security. When you begin to like mix and match them to have them cover the weaknesses of each other, you can achieve great improvements and like quantum leaps in the form of expression, not quantum computing, right? In terms of like verifiable compute. And yeah, that's it.
Okay, yeah. So one thing you mentioned, I think I'm 100% agree is like T is like a glue, right? You can glue T with like AI agent, and you can get a real AI agent, not fake AI agent. And you glue T with say a Web 2 program, then you get Web 3. So Web 2 in, Web 3 out. This is something we used to mention before. But I would like to bring some specific take here. So my expectation is that within maybe 2 to 3 years, within Web3, everything running now on AWS, I think should be moved into TE or maybe AWS TE as well, because there's just no reason you're still running anything on some server that's not as secure as TE, given TE is already there and it's very accessible already. Think about the Bybit hack. So it's the largest hack happening in the recent days, the entire industry. All the time, yeah, all-time high. So, but which part gets wrong? It is the front end. Yeah, nobody will even think about we need to use something to secure the front end because everyone just assume front end is okay. You can compare your own front end and then you're okay, right? But it turns out it's not okay because in the whole supply chain, or I mean, when you are using like a ledger, you are not just using ledger, you're also using the blockchain, the smart contract, the front end, the indexer, your computer, right? Any single point in this phase get failure, then you can potentially get wrecked. So all-time high lose. So now if we put all those steps instead of running in a normal server but running in a TE, then we can actually let those components to test each other. So you can have interoperable security. Then it's not going to dig into the detail, but basically if you put your front end in the TE, then front end will not be hacked that easily. And if you put the indexer in the TE, then you can get end-to-end security between the RPC and your hardware wallet. So why not, right? But even take that one step further, we start to work on TE because we think that blockchain is great, but blockchain cannot solve everything, right? What if in the future Web3 can even eat Web 2? Then we need something to glue the Web3 and the Web2 part, the glue you mentioned, right? I think TE is the perfect glue to bring Web3 to Web2, or maybe in the future, once we solve all the trustless problem, the trust problem with either on-chain smart contract and the TE and other like FHE, MPC, ZK, then we even don't need to have a word Web3, right? It's just the new web. Everything can be trusted and can be verified. So yeah, that's my spicy take.
So I think I need to go next. So I wish AWS listened to me, but the way it works at AWS is we always work backwards from the customer. Our customers tell us, like, this is what we want. This is what, over 90% of the AWS products are built because customers tell us something. Oh, this is what we want. This is what we would like to do. So answering the core question, like, what do you see in the future coming up? Like today I had like 2 different customers. We have like probably many of you having back-to-back meetings. The main question was like, okay, how about the GPU support? Like, okay, now we want to use GPUs with T. So it's increasing. So in the past, it was like a great finding for us. Oh, we can use it in any of the compute that we are offering in the next gen of any offerings. Now suddenly the demand has increased. Now the customers are asking, now we want it on GPU. Now we want it here. So the demand increases, and I think the companies like ours are responding to what customers want. We always act on the customer's demand. And just one side comment to another thing that you said is like on the front end piece. I think within the development and things, we forget because like in the past it used to be very important the front end because the front end was fully loaded with heavy clients. So file integrity monitoring, like the basic PKI, was the key thing that everybody integrated into every security project. And later you say, oh, nothing is happening there, probably it's not too important, we just skipped. Now this thing happened last week. Oh, technically we should be focusing back on the front end. So it's also cyclic. During the development of things, we forget the important parts. So,
yeah, I think one thing I'm looking forward to is, so we'll be launching something called Campaign APIs. It allows AI agents to observe and actuate the real world. And when we go into a future where AI has, or something running on a computer, has a power to request something, some random action in the real world, you want to make sure that there are appropriate laws which are always followed so that it doesn't do harm, right? And that would really require a verifiable form of compute, a compute that I can trust. So I see the future is very bright for TEs.
Awesome. Well, thank you so much. Thank you, everyone. Thanks for the AGI Summit for hosting us. And yeah, next panel soon.